introducing you, Laura. So we're at about 136 people, which is about right for a School of Chemistry seminar. So welcome everybody to this seminar on a third week are we in now? And it's a real pleasure to introduce Laura McKemmish. And this is a particularly special seminar because it's the first seminar of the year that we've got a speaker from within the School of Chemistry. It's a great pleasure to welcome Laura to present her recent work to the school. I'll give you a bit of a background of Laura's biography. Laura did her undergraduate degree at the University of Sydney and then went to the Australian National University for her PhD. After that, Laura went to London for a postdoc where she was the recipient of a very, very prestigious Marie Curie Fellowship. And then I think it was in 2017.
2018, I started.
2018, sorry. Laura moved to UNSW to start her independent career. Whilst at UNSW, Laura's research has really taken off. I think one of the most notable things for me in seeing some of what Laura has been doing research-wise was how presumably some of what we may hear about today really came to the fore last year or the year before when we learned about phosphine in the atmosphere of a planet, and suddenly it was really quite amazing to know that there was someone in the school here who was working on a very similar area and ended up contributing to that research story, I think. Laura also contributes heavily in teaching and in particular in outreach, where Laura leads the SciEx program, which kind of engages now, or has engaged over its course, I guess, hundreds of high school students, and hopefully providing them with an introduction to science and maybe a pathway to coming to do a chemistry degree. And maybe there are some people in the audience, maybe, who...
Not quite yet, but in my first year class, there is.
So there may be people in the audience who have siblings who have done SciEx. We can go for that, or children. So after starting here in 2018, Laura was last year in June 2021 promoted to senior lecturer, and this seminar is, on the one hand, an excellent opportunity for us all to learn more about what Laura is doing at UNSW and her research and her teaching and service, but also really an opportunity for the school to come together to celebrate Laura's promotion. So with that long introduction out of the way, I'll stop sharing, and Laura, please take it away. Oh, and I should just say again, this is being recorded. So you saw that on the slide. Sorry.
Yep. All good. You can see the slide? Excellent. So I'm going to start with an overview. One of the things I found that was really important in my first few years of my independent career is really defining myself and where my research direction was focusing on. And really, this is the accumulation of 4 and a bit years thinking on that. So sorry, I'll get to the next slide. So what I'm going to talk about today sort of goes through 6 things, and we're going to focus on the research, but I am going to talk a little bit about the teaching and the service that I do, because it is actually, to me, very much an integrated story. It's going to focus on astrochemistry, the data needs there. We're going to start with some very high resolution, high accuracy subwave number results, then go to approximate stuff. And the predicting vibrational spectroscopy using computational chemistry is really a take-home message for everyone in the audience who's ever done hopefully something better than a B3 LIP 631 G star vibrational frequency, but we'll tell you what sort of accuracies you can expect from that. And then I'm going to tell you a little bit about the teaching and the outreach that I do. So, big picture, astrochemistry. Astrochemistry is the study of molecules and ions occurring in planets, stars, interstellar space. Basically, whenever you look up there, the only information you've got is spectroscopy or photometry, but I'm really interested in the spectroscopy because that tells us about the molecules in the system. And so really spectroscopy, in the way I do it, is about getting down into the really deep details. So this isn't the spectra you do in first year chem. This is thousands of spectral lines, millions of spectral lines. This is the sun spectra. And honestly, this is simple compared to the high resolution data that sometimes we do. So when astronomers are analysing these sort of spectra, they need data and good data from both computational chemists and experimental spectroscopists. And in many ways, look, I do the computational chemistry that leads to it, but I also do quite a lot of work in bringing those two things together to produce a model that the astronomers can then use for their data. So that's going to be the first part of the talk, describing how that happens and what I'm contributing. So in particular, what the astronomers are looking for is something called a line list. So a line list, think of spectroscopy, the way I think about spectroscopy is energy levels and transitions between them. And a molecular line list is essentially going all the energy levels you can find in that molecule, and then the intensity of all the transitions between them. So often that's hundreds of thousands to millions of energy levels, millions to billions of transitions. These line lists are huge. And that data is used for absorption spectra at different temperatures and pressures. I'll tell you about the molecules I focus on later, but this is a really broad research effort that's absolutely essential for any of those news articles you say going, what's in this star, what's in this exoplanet, what's in the interstellar medium, we've found this interesting molecule in space. All of it relies on line lists. And one thing, just if I bring your attention to the second figure here, computational chemistry that many of you will be familiar with is normally designed around finding ground state properties, solving the electronic Schrodinger equation, getting potential energy surfaces. I actually go one step beyond that and solve the nuclear motion equation. So we go beyond the electronic, beyond the Born-Oppenheimer approximation, and we actually sometimes have multiple electronic surfaces, and we're calculating all the vibrational and rotational energy levels there up to pretty much dissociation. So one of the big topics in astronomy at the moment is exoplanet atmospheres. So imagine that, well, you've got a star, it emits a rainbow of light, and then the atmosphere of a planet absorbs some of that light, and then we see it on Earth and we see an absorption spectra. If I was to say one of the big goals in astronomy at the moment, it's finding molecules on exoplanets so that we can identify ultimately life, but that's a little bit down the track. In the meantime, identify what these weird planets are like. So we often know what the dominant molecules are, so water, carbon monoxide, so on, but there may be very weird molecules. So the ones that I've actually focused on a while ago, 2019 is when I published the last one of these. M dwarfs, so sorry, on the right here, there's a cool star. So cool stars have molecules. So hot stars have very few molecules. The cooler the star, this is about at 3000 Kelvin. It's got this weird diatomic molecule called TiO. The other thing that's important is hot Jupiter exoplanets. So imagine Jupiter, bring it really, really close to the sun. Those gas planets are the easiest to see. Therefore, we're going to look for molecules in them first before we're looking for Earth-like planets. Turns out TiO and VO are probably some of the molecules there, but honestly, they've been arguing about it for a while, and they're waiting for better telescopes and better data, which is what I'm producing. So look, the ultimate goal is to search for extraterrestrial life, and it really relies on molecules in the atmospheres of planets in sufficient abundance that it can only be attributed to life. So often, it's not so much what life produces, because life produces a huge array of chemicals. It's often what geology doesn't produce or what isn't destroyed. So if I can bring it back to phosphine, phosphine's exciting because, look, it's not produced by Earth life a lot, but it is a little bit, and it's destroyed really quickly and not produced by geology. And that's why it was so exciting to potentially find it in Venus, because it wasn't produced by geology. So molecular data, just re-emphasizing the point, is essential for the astronomers to interpret their data. And I just want to show you, this is probably one of the better signals for low resolution of detection of TiO from space observations. So the dots with the vertical error bars that are very large vertical error bars, they're the observations from probably Hubble over this wavelength. If you look at earlier spectra, they had horizontal, huge horizontal error bars as well. So this is actually really good comparatively, but you see that we're not getting a lot of that detail. But there's enough that people are somewhat confident there's TIO. Honestly, they keep arguing about it, but water, they're pretty confident in quite a lot of systems. This is the low resolution data. Now, this is the slide from a few years ago. JWST will launch soon. Let's just wait. And it turned out it was a really nice Christmas present. It launched, it's going to get data up soon. And really, this is going to bring in a new wave of interest from the community on exoplanets, molecules, and that's what's really driving a lot of my research at the moment. So while the astronomers were waiting for JWST, they actually got sick of waiting and figured out that if they used really, really high resolution ground-based instruments, they're going to get really bad signal to noise. But if they have thousands of peaks and figure out, well, here's what it should be and here's what it actually is, you can get molecule detection if you've got high quality data. And someone tried that in 2015. And so the top curve here is the observed data. This is actually in an M star. This is one where we know there's TIO because it's a star. There's definitely titanium oxide. The top black bar is the data. And the three bottom ones are the predictions from models that were around in 2015. And as you can see, a lot of the peaks and troughs don't match each other. So if you're trying to find TIO signal through any of the orange, green, or blue data, you're just never going to find TIO. And the reason for that is that the scale on this thing is about 0.35 wave numbers. It's just really, really accurate. And so someone wrote a paper saying, basically, we can't find TIO because the line list isn't good enough. And that motivated my work. So the reason the line list wasn't good enough was because there was 13 or even more electronic states at very low energy. So 20,000 wave numbers, for those who can't, that's about visible. So any transitions on the right-hand side, all these different transitions, all the named bands, they're present and important when you're trying to model TIO. Most of them are in the visible. All the coupling between the electronic states, there's Born-Oppenheimer breakdown going on here, there's spin-orbit coupling, it's a mess. And so what we actually found out was that if you try and just do electronic structure theory, so you put this in Gaussian, QChem, whatever, honestly, errors are far too big. You're getting nowhere near sub-wave number. You're often getting 10 wave numbers on vibrational frequencies and hundreds or thousands of wave numbers on electronic states, which means it's pretty useless. However, the dipole moments are critical because they tell you the intensity of the transition. So we combine the dipole moments, which we get from theory, with the experimentally determined energy levels. There's a procedure called MARVEL that I'm not going to talk about now, but basically it takes all the experimental data and tells us where the energies are. We combine them together in a nuclear motion program. So that's solving the full Schrodinger equation, not just the electronic one like most people do. And then we put that together and we get an XML line list. My titanium oxide line list had more than 300,000 energy levels and almost 59 million transitions. And then we test it. So this up the top is experiment and down the bottom is theory. And what I'm really proud of is, look, the strong lines, honestly, we'd probably expect to get them because we probably put them back into our data in the fitting process. But all these weak lines at the top that you think are noise, they're isotopologues. So if we actually put the isotopologues, by which I mean titanium 46, 47, 49, 50, if you put all that data in at the right percentages, we reproduce the experimental data beautifully. And I have to say that was a really nice moment when I saw this one. And turns out the astronomers use this data a lot. The papers actually, Google gave me a notification saying it's been cited 100 times this week. So that was kind of exciting. But yeah, it's needed data. And what I love is that you're doing all the cool spectroscopy and producing data that people use. That's the best combination there. And I think here was a review paper I wrote last year on molecular diatomic spectroscopy data because that's sort of become my thing. And data users are obviously the result, the one we want to get to. But I think it's really important to recognize that experimental data producers are essential. Ab initio quantum chemistry people are essential. And there's a two-way pathway. So the data users tell the experimental data producers, hey, we don't have data for this. Can you go and find that, please? And then they tell us, theory, we don't know what this is. We've got no data here, and it goes back and forward. And then the data modelers, which is where I classify myself primarily, go back and forward with the experimental data people and theoreticians going, we'd like this, don't really need that. And then we go back and forward and then ultimately produce data for astronomers. And then we sit there and say, this bit we can trust, this bit we can't trust, this is our error bar, and that collaboration with astronomers and trying to ensure they understand why water spectroscopy is much more known than titanium oxide with all its electronic states. Okay? And for best results, we really need that synergy communication. One of the biggest barriers I've faced recently is people produce excellent new data for TIO, and I'm like, great, but then I've got to somehow convert it to the astronomers. And so, and the same with the ab initio people, they sometimes produce curves and don't put the raw data behind it. So this is a message for everyone. Please use your supplementary information, put your raw data, don't just put a figure, because a potential energy curve is a figure I cannot use. Potential energy curve where I've got all the data points, I'll cite your paper, I'll encourage everyone else to cite your paper. You can show the relevance, but a figure I can't use. So that is a really general lesson. And we've evolved. So when we did TIO in 2019, when I did TIO in 2019, we had variational energy levels and we put the experimental data in there, and that was the state of the art then. But Anna, my PhD student, recently tried a new approach where we actually had 3 sources of data. So we had variational energy levels, that's the gray. So they're what our model, when we put in all our potential energy curves, we put in our dipole moments, we solve the nuclear motion Schrodinger equation, we go round and round and round. We get a set of energy levels from our model. Then we have experimental energy levels, so they're marble. And we've got these things called perturbative energy levels, which you actually know, they're model Hamiltonians. They're your Omega BE, Omega Chi, all those sort of things give you model Hamiltonians. Variational, by the way, is what you get when you put in the potential energy surface, you solve the nuclear motion equation properly. And we actually combine them all and use the advantages of all of them, and they're really complementary. So variational extrapolates well, perturbative interpolates well, and experimental is the best source of information, but reasonably limited. You normally only have thousands, whereas you need hundreds of thousands of energy levels. Cool. So how does this work in practice to try and find aliens? And as Martin alluded to earlier, we've actually got an excellent example here. So I'm going to show you a video that was an interview that I gave in 2016. This was university student created video. It was kind of fun. Yeah. Probably 30 years we'll find something that looks like a biosignature, and then we'll spend at least the rest of my life arguing over whether or not it's a biosignature. So that's what I said 2016. And what was really ironic, and I only figured this out when I was screen capturing something, is look at what is in the background, phosphine. So phosphine, 4 years later, I had no idea at this point. It was one of my colleagues, Clara, who gave a talk last year, who was Dr. Phosphine. I was doing TIO and VO. So phosphine became the center of it all. And why phosphine was really important was because it shouldn't be present at the abundances that were detected. And therefore, if you include volcanoes, you include meteorites, all those sort of things, in the environment of Venus, it should just react and go away. It's the same reason on Earth, oxygen shouldn't be present if there wasn't life. It would just react with everything else and just go away. It was detected in 2020, and I did some stuff about that. Now, I will say since then, as I said in 2016, there's been a lot of arguing. Look, I don't know where the state of it is. You'll have to ask an astronomer. It depends who you ask, I'm sure. There was some problems with the telescopes, and one of the other, so the data processing basically, but the other problem was that people thought, hang on, it might not be phosphine, it might be a different molecule that we don't have spectral data for. So look, this happened in the microwave. I'm going to bring our attention to the infrared because that's what I've focused on. But if we look in the infrared, this is a plot of ozone, the spectroscopy of ozone at low resolution. So this might be what you expect from something like Hubble, maybe JWST, who knows. And then what NO2 and methane and H2O2, if you're only looking at that 1200 to 1400 wavelength region, you don't know which molecule it is too much. Like if you've got a low resolution spectra, you don't really know which one it is. And it turns out there's 600 other molecules that they think might be present in atmospheres. They're not sure, but a big list of molecules. The thing is that we don't totally know it's phosphine because, and we don't totally know when they find a molecule that it's what it is, because there's about less than 100, I would say, molecules with sufficiently accurate data that we could detect them. And even then it's a bit, how you're going. But there's thousands of molecules that could be of interest depending on the atmosphere. And so the way that we actually address this is figuring out, what about if we go from the high resolution and go the other side? What if we go moderate resolution and go as accurate as we can, but we're trying to do it for thousands of molecules? And I just want to talk first about the infrared spectra. You guys, I teach my first year students how to do this. Literally, I did it. Well, I'm doing it at the moment. We build a molecule in some sort of web interface. We put all the options in and I tell them what to use, and I go, Hartree Fox, not good, but I can tell them what to use and figure out what happens. You run the calculation, you get some vibrational frequencies, you get some infrared intensities. So this sort of data is the first thing we need for a line list. And then we can, just because it's cool, we've got the OH stretch here, and we know an OH stretch doesn't take place at 4,000 wave numbers. It's far too large. We actually need to introduce scaling factors. So this is mimicking the anharmonicity, very, very standard. You calculate anharmonic frequencies, you apply a scaling factor, and then you produce a spectra. So I can do this in about a minute, and I can teach my students how to do it in probably 2 hours or less. Great. Now do this 10,000 times and tell me what errors you expect. And one here accepted the challenge and started a PhD. The 10,000 molecules were molecules that could be of interest for biosignatures, but really you can do it with any set of molecules. And his goal is to obtain spectra for thousands of molecules that could be interest. And we're trying to do high throughput calculations, get approximate spectral data, get it as good as we can, but he's got 3 years in his PhD, 3.5 years, whatever. And that's how long he's got. So his approach is, first of all, you're not going to use a graphical interface and you're not going to build each of the molecules. You're going to start with something called a SMARS, which tells you a molecule in a language a computer can understand. Then you put it into a Python program and you say go, and it produces initial geometries. Then you can generate the quantum chemistry input files, that's some Python script. And then you run the calculation, you get to the end, and then you check the output. I think it's about 90% of the time it just works. 10% of the time you have to go and do something fancy, but a lot of that you automate it. We're sort of trying to make it more automated, but it's not too bad. One hasn't killed me yet for asking him to do this, so I'm going to take that as a good sign. And then you get to the output file, you do your data analysis and visualization, and you get your spectra of your molecule. So that's what he actually did. He did this immediately after the phosphine detection, and we actually generated data about 2 months or something to do all the phosphorus containing molecules. So that was our first guess. And then we got the data and we're like, okay, so what are our errors here? What can we do? Oh, actually, sorry. The first thing we did was, what's the use of this data? I think it's interesting to characterize spectral congestion within a given frequency window. So one thing that I found for phosphine, for example, was, one found for phosphorus containing molecules is the pH stretch is at a beautifully clean window of the infrared spectra. It's about 2,200 wave numbers, which is great until you realize that the CO2 absorption is at the same frequency. Not so great. You can identify molecules with strong absorptions. And then, because say TiO in the exoplanets, it's not like TiO is the most abundant molecule. Like, it's pretty abundant, but it's not the most abundant molecule in the planet. It's abundant, but it absorbs really strongly exactly where the star gives off light, and therefore it's the most important molecule in M dwarf spectra. Providing data for machine learning applications. So it's really going to be a future work section for one. But anytime you've got this high throughput data, we've figured out what CompChem can do. If you remember Clara's talk, she was telling you what basically organic chemistry functional groups can do. We're doing quantum chem, and then the next step is to see what machine learning can do, figure out what's best and go from there. It is important to note this moderate quality data is not going to be good enough for definitive molecule detections, but I think it's playing an important role in complementing that high accuracy data we have. And it's an underexplored role. Astronomers literally can't find anything if they don't have data. So we need to give them something. Otherwise, they just assume that their list of however many molecules is all the molecules that are out there. Okay. And with all due respect to many astronomers, they haven't necessarily done first year chemistry and realizing that an OH stretch doesn't just mean water. It could mean lots of other things. Some astronomers know that, but not all. So one thing that was really important to us once we'd done the original data is going, what model chemistry should we use? Should we use B3-631G star, like Radham and Scott told us to do in 1996, or should we do something more modern? And the first thing we did was we compiled the literature, and Juan's amazing and compiled 1,400 scaling factors. And basis set is on the x-axis, level of theory is on the y-axis here. Don't worry if you don't understand all of these. It's mostly for the specialists in the audience. But what you can understand is on the color axis, this is the root mean squared deviation between the scaled harmonics and the experimental frequencies. It varies between about 20 wave numbers and 40 wave numbers here. The 20 wave numbers is probably the limit within, it's the what we call the anharmonicity error. It's you're using the harmonic approximation and scaling it, you can only get so good. It does matter what level of theory and basis set you do, but there's a lot of gaps here. A lot of the modern methods, a lot of the modern basis sets haven't been tested. So this was the first attempt figuring out what was known in literature. And honestly, we said, look, it's useful, but it's not, the problem's not solved yet. So let's do some more work on it. And that's where we came up with this VibeFreak 1292, which is a benchmarking database that replaces the most common older one was done about 30 years ago. So we compiled all the ones that were out there, updated all the frequencies, checked with all the new experiments. We found some errors, a lot of it was fine, but some of it was off. And then because we couldn't, because we wanted to understand the minimum error you could get if you scale these anharmonic things, if you scale harmonic frequencies, what's the minimum error you can get? This level of theory is essentially pretty close to, it's not perfect, but it's pretty good. Very high level theory, way beyond what you'd want to do in a routine calculation. So we compare these using scaling factors. Now, if you consider the whole frequency region, you've got a scaling factor of 0.9617. And this is the error. So experiment versus scaled theory on the y-axis, and we've got a box and whisker plot. The median error is 16.1. And interestingly, if you do the RMSE for this, your RMSE is about 33. And I would say that 33 is not, if you're doing a calculation and you go about how much should I expect my number to be out, I actually like the median for predicting you're doing a random molecule. Your frequency predictions are about 16 wave numbers off, versus doing an RMSE of 33, which is only where 33, these box and whisker, it's about 20% of the data has a error above 33 wave numbers. And that's because the small number of outliers that meant we had to do this weird double axis scale up here. There's lots of outliers and they just dominate. But if it's an outlier, you're probably going to figure it out some other way. Maybe it's a problem with the experiment. Maybe it's a problem with the theory. We'll see what we're doing. But really interestingly, if you introduce scaling factors separately for a low frequency, mid frequency and high frequency region, you reduce that error by more than 50%. And the RMSEs only actually go from 33 to 29 because they're dominated by those big ones. But if you do the frequency specific scaling factors, you can get that error less than 10 wave numbers, which is pretty exciting. So what should you do for now? What level of theory, what acronym soup do you want to use? This is our recommendations for now. It's based on the scaling factor review. We actually need to do a current extensive benchmarking, which is what Juan's doing at the moment. He's getting all the data. You'll have to see me talk in the future, or just send me an email and I'll let you know what we come up with in about June, hopefully. Cool. So I just wanted to summarize this bit and talk to you about the big picture. If you're thinking about molecular detection in astrochemistry, in general, regardless of the spectral region, what we've mostly been focused on is high accuracy data for sort of order of 100-ish molecules. You do laboratory spectroscopy, well, sorry, this was for a grant. So laboratory spectroscopy on a smaller number, but it sort of goes back and forward depending on what you're doing. And then astronomical observations on a smaller number of molecules. But what we're really adding here is a better way to do the high accuracy so it can cope with new things, and the high throughput method. So high resolution data is really essential. It's challenging but rewarding. And one of the things I love about this field is I've got people that literally come up to me in conferences or give talks before going, we need this data. And I'm like, okay, I'm doing it, we promise. That usefulness, I don't really mind what molecules we do. They're all chemically interesting, but if they're useful, I'll do that one first, thanks. And I also just wanted to emphasize this is a really strong experiment theory synergy, and we need that communication to be strong. We need it to be ongoing. So when there's new theory, new experiment, it updates the data. I think that pipeline needs some work, but we're getting there. And we're also talking about the high throughput predictions of hundreds, thousands of molecular, infrared, and microwave spectral data is possible, useful, and that's sort of where I'm pursuing both with Juan's PhD and a student coming in T2. We're hoping for a median accuracy of 10 wave numbers. I think if we can get our DFT method right, we'll see how we go. And just that spectroscopy is awesome because it allows us to do all sorts of cool things. So this is the research part of my talk, but the bigger picture again is really it's the students. So I've mentioned Anna and Juan a lot in these talks. They're my PhD students. They did a lot of the work I spoke about today, but I've been blessed with a whole bunch of other students who have come in, honours projects, undergraduate research projects of various lengths. They've done so much work that I couldn't possibly put it in a 45-minute talk. So I'm just going to have to say thank you here and just recognise that thank you is the main thing I wanted to say there. But the link that I wanted to bring there is some of the Claude's did an undergrad project with me, came back for honours, now doing a PhD with Martina. Some students stay in research, but not all of them do. And so I want to make sure that we're teaching all of our students, and really this is a link onto the teaching stuff. So I believe in training students in computational chemistry, Python as a form of computational thinking, programming. Python's just the easiest one to do, and creative research. So the big advantage of a computer is I can let a high school student or first year student go, just do whatever you like, put any molecule you want, just go for it. You cannot do that in the lab, so for obvious reasons. So I've actually tried to encompass that in the teaching that I've done. In the first year, I've developed a series of mastery workshops. Oh, no, we call them professional skills workshops. Sorry, professional skills workshops. We actually teach them Comp Chem, essentially what I showed you earlier. We teach them concepts, and really I use it as a way to encourage independent investigation. So they're proving BSEPR theory tomorrow they figure out 2 molecules they can do that strains BSEPR theory. I want to put this in the context of research, of teaching that's not done by me yet. I'm going into physics chem this year, but Python notebooks that are doing data analysis, visualization. At this point, it's normally, click through the thing, change a few numbers, not much actual writing of code from scratch, but it familiarizes students with it, which is really, really important. Third year Comp Chem, I designed a notebook for students to learn how to write a Hartree-Fock code, which is, I think if you understand Hartree-Fock, you understand most of the mathematics behind quantum chemistry. We do some IQ mol, integrate it that way. And then with Martin, so it's nice that you're on the screen there, Martin and I do a Python for chemistry course in 4th year that's audited by a lot of honours students, that's really aimed at taking wherever the students start, increasing their Python knowledge, and giving students the confidence to write programs to solve chemistry problems, and really the confidence to Google and ask for help and all those sort of things. Long term with this, I actually see, I'm in discussions at the moment at a faculty level to see, well, physics are trying to do similar things, Babs are trying to do similar things, Bs, etc. How can we integrate this and try to form a bit more coherent conception of how do we put Python and computer knowledge into degrees? And the reason I mention that is if you're interested in it, either on a chemistry level or on a broader level, please chat to me if you haven't already, because I think this is, well, I think this is really important. And yeah, based on the number of people that we've seen integrated into our honours course, programming is definitely something a lot of people are doing now. So when we talk about we're training students in all these things, we also train them with research. So research integrated learning is something I'm a huge fan of. And I actually started as early as year 12. So this is the introduction to the SciEx program. A SciEx project has to have a team, a context, research tool, and a hypothesis research question. And for a concrete example, I get Anna one, I sort of sit in the background and help out when I'm needed, which is not very much at the moment. And then we've got high school students. These are our 2020 cohort. 2021 and 2022 have been online, but we've got about 20 more students or so. We teach them exactly what you showed before, how to calculate an infrared spectra. We give them a context of bushfires, exoplanets, Earth, climate, things like that. And then they use that to identify a hypothesis research question. They identify some molecules that they're going to calculate spectra of. Then they figure out this molecule absorbs more than this molecule. You can see this if there's CO2 in the atmosphere. You can't see this if CO2 is in the atmosphere, so on. This is the creativity. And CompChem enables this creativity, this scientific thinking, problem setting, not just problem solving. And I liked this so much. We piloted it in 2019 and we went excellent. And Shannon Maisie was really big in the first year for getting this up and running. So thank you to her and lots of other people. I can't mention them all. So now we've got the SciEx program. So the SciEx program is a high school 1 week summer school where students do research with PhD mentors in groups, and it's linked with the Science Extension School syllabus. And I'm fortunate enough to have a nice video, hopefully, so that I can stop talking for a minute.
We're here at UNSW taking part in the SciEx program at the moment.
And I'm here at the Science X UNSW course.
I'm here at UNSW to do the SciEx program for Extension Science.
So I'm here at UNSW in Sydney doing the SciEx summer school program. The project we're doing at the moment is exploring...
This is Anna Wang's lab.
So the benefits that I found joining SciEx at UNSW, I really enjoyed how well organised everything was. And I really felt that I worked well with everyone here, including my mentor and my lead academic.
It was really cool. Spent the whole week here, used telescopes during the day, didn't know you could do that.
Hands-on to make it like the best possible experience for the student.
And it's really cool how we've got a PhD student and a professor here helping us work on it, and really nice people. From what I've heard from other groups who are doing other things, it's really cool. They're really excited about what they can do with the Science Extension program.
And I'm here at UNSW doing the SciEx summer school program.
So that's the big picture. Basically, that had a lot of really good graphics to show you that this is taking part across the Faculty of Science and beyond. 2020, we had 65. 2021, we had 92. And this year we had 176. We were forced to go online last minute, which was annoying. But next year, crossing fingers. But to make this work, I'm not going to go into a lot of detail here, but project design is crucial. Getting that project right, you've got everything else, but the project is hard. Program structure so that we can actually design it for the context. So I'll just leave it there. Funding, always important, and scalable. So we've scaled this up to 176, we'll scale it bigger, and it's about making sure that it's hierarchical structure so it all works, and that I have time for research and other things, which I have. So this is some more images about the summer school is really the pinnacle of the program. They learn research, explore the hypothesis. They see research beyond their own group and really experience life as a university student. I will highlight that it's a very EDI friendly approach. We had 40% fee waivers, which caused some budget issues, but was approved by faculty. Thank you, faculty. And 68% female enrollment last year, which was, I didn't do any targeted recruitment, so that was exciting. Students love it. So on campus, we were 4.9 out of 5, which is student satisfaction scores I have never got. The research time with the mentors was the big thing. So actually talking with their PhD students, engaging with them, that was the key. They increase their self-identity as a scientist. So basically you figure out how much do you feel like a scientist. And at the beginning of the week, it was about 3.8. And at the end of the week, it's sort of 4.7. I think we did even better 2022, which is exciting. And then of course, it's all the skills. Computer skills are there deliberately because computer skills are skills students don't think they need, but they do. So it's also really beneficial for the mentors. So this is the 2020 photo. Now we've got about 30 mentors involved. Look, it's outreach. You talk with students, you make a difference, increase STEM literacy, all that sort of stuff is awesome. They're fantastic students. You get these incredible questions. It's amazing. Skills. The skills beyond their research that I think are really important for them getting a job, CV, and we pay them. So in terms of training researchers, I actually think that we do this I wanted to show this because I think it sort of brings the talk together. This is pictures that were taken of me supervising high school students. This is in the UK because they're the best photos I've got of this. And really, I love working with students to do research. And I loved the experience as a student, and I love it as an academic when I can support all these different things. And so I just wanted to sort of do a mission statement almost, facilitating students to become strong, independent, curious, and creative problem setters and solvers who are power users of technology and ready for any job. So that is what I hope to accomplish. And I think there's a really nice progression pathway that I've been involved in. So SciEx, mastery classes in first year advanced chemistry. We actually have interviews with researchers. They give mini talks. Undergraduate research, I've co-course coordinated since 2019. And of course, I've had honours and PhD students. So that progression, I think, is really fantastic. And together, with all these great students that I've had and hopefully will have in the future, if we use all these awesome things, spectroscopy, computers and technology, we're solving the problem of trying to find aliens and many more beyond that, was just the one that looked pretty. And yeah, these are the things I talked about today. And I hope I'm not screamingly over time. So thanks.
Thank you very much, Laura, and no, perfectly on time. People in the audience, please do kind of show your appreciation with the clap reaction, I think is what it's called on Zoom. And whilst everyone thinks about whether they have questions, or you can use other reactions, as Anna just did, the celebration reaction. I'm going to make it so that anyone who wants to shortly will be able to unmute themselves and start video to ask questions. But Laura, thank you very much for a really fantastic talk. I might go straight into questions because there's a question that's come through already from Tim Schmidt, which is, I think, kind of when you were talking about your orders of magnitude sort of slide towards the end of the astrochemistry part, the you know, the calculations versus spectroscopy, experimental spectroscopy. Tim's question is, what molecules are the highest priority for actual lab data?
Oh, actual lab data. I'm not entirely sure, but I'm writing a paper that's due in April on that. So I'll be able to tell you then. I haven't looked at it recently. It's normally like very specific. It's like this band of this molecule. I'll send you the paper when I write it, Tim. It's designed to answer that question well.
While we're on this slide, I might skip ahead in the question order to Chris Hansen's question. Oh, that's come through privately. Chris, you can ask your question if you want when there's a gap. Although I share the question. Why is there a dog?
Ah, because it's Toto. This is Toto. Did I not give you the name of my TIO line? My TIO line list is called Toto because I don't know, it was like on McDonald's, TIOTIO, I think was the thing. So it became Toto. We need a name for the line list, so that's what it became.
Okay, that makes sense. Question from Kenny Liu in the chat, which is about the scaling factors, splitting up the scaling factors based on wave number ranges and how this improves the median uncertainties. And Kenny asks if there's any value in further partitioning those wave number ranges.
Good question. We haven't explored further partitioning. We did explore changing the wave number ranges a bit. We didn't want to go too much. So at the moment, there's global or a low and high frequency. So introducing 3 seemed reasonable, but yeah, there's options.
Could I also ask on that? I had a question on that slide as well, which was around how did you arrive at those numbers? Is that through a fitting process?
Oh, how did we arrive at the numbers? Less than 1,000 was what everyone did before. So there was a cutoff low to high frequency. The 1,000 to 2,000, oh, I think it was we tested up and down and figured out the fact that these scaling factors are reasonably different and reasonably even from each other, I think was part of it. But I think you could argue 2,500 if you wanted to, it just wasn't quite as good.
Okay.
Yeah, I think there's argument there.
And I guess there's another question here from on this slide from Chris Medcraft, which is asking, is there a physical origin for the scaling factors, and asking what theory is missing or ignoring here?
So the theory that's missing is the anharmonicity. So we're assuming when you calculate these frequencies using Gaussian, QChem, whatever, you're calculating a second derivative at the origin, which gives you omega E, but it doesn't give you omega E chi E. But on average, omega E chi E is some fraction of omega E. And so this is actually representing the anharmonicity that's present in each of these modes. And I will say one thing interesting, the scaling factor for the stretches, there's more anharmonicity. So the stretches are high frequency ones. There's more anharmonicity in the high frequency than in the low frequency, which tend to be bends and bigger motions of the molecule, which is almost counter to, often we go low frequency modes are more anharmonic. They're just less reliable is what this data says. They're less anharmonic, which I think is counter to at least what I was saying. And then I looked at the numbers and went, hang on, that's not what the numbers say.
Yeah, that was interesting. Yeah.
Might have to think more about that one and check that it's but
there's a question on SciX from Oscar.
So we'll get I'll do an EOI in about May, June. Chris Killian as chemistry outreach coordinator now, so he took over this year. He's going to be in charge of which chemistry projects go up. I'm on the coordinator level, so I'll review all the projects. Your supervisor needs to be happy about it, happy with your participation, that your PhD is going okay. The time commitment, the first year is probably about 60, 80 hours. After that, it's more like 30 hours for the next few years. The first year setting up the project takes a bit of time. But yeah, we'll do a call May, June, and then check that the project's suitable and go from there.
Awesome. Next one is from Sam. There's a lot of questions, which is great. It shows that people have really been listening and engaging.
Well, you started it, Martin.
I don't. So Sam's question related to the teaching. How equipped do you find? And I shouldn't skip over the compliments that it was a great talk and great to hear about the broad range of things you've worked on. Question related to the teaching. How equipped do you find that current students are for computational and programming work? And do you find that like students, undergraduate students, honors students, maybe pick programming up more quickly than established researchers do?
It's an excellent question, and I think there's some people that think computationally and pick it up fairly naturally. I mean, often it's whether you automate things in computer games or whether you debug your phone and Google things and pick up stuff, but some people definitely find it very challenging, and it's not always easy to predict who's going to find what. One of the reasons for going for a faculty-based approach, and what we try and do in the 4th year Python course, is cater to different students. So some students will need that support all the way through because programming doesn't, the thought process behind it, they haven't come across it before, it's not as natural. So we want to support those students as much as we can while still letting the students that love it pick it up quickly, maybe you're doing a computer science double degree, that we help them too. I think with academics, you'll find, or more experienced researchers, look, I think some people obviously struggle to pick it up. It's probably a time commitment thing as much as anything. But a lot of, when you talk to people around my level, they'll all say, I'm all self-taught. I picked it up by Google. I'm not really that good a programmer. And everyone says that, and everyone's brilliant. So the thing is that, look, I'm not saying we should go into a computer scientists have all these skills, but scientific computing is a different set of skills that I think researchers are very strong at. It's just finding that balance. That's why it's so hard to teach.
Yeah, absolutely. Maybe I'll take this as the final question in the formal Q&A, but we can always do more questions afterwards, if that's okay with you, Laura. And it's the question from Survey, which is, when it comes to the high throughput spectral project, what's the process? How do you decide which molecules to include or exclude from your, what, 10 to the 5 molecules,
Yep.
was it?
So the molecule list we're working with at the moment is one created by Sarah Seeger, who's an exoplanet, and her team, who's an exoplanet specialist. They're molecules that are organic, not too big, so likely to be gas phase. And I think they did some cutting for molecule, like they made all the valencies and made all the organic-y type molecules, and they got a list of 16,000. And we thought, well, they've spent all the hard work on that. We'll just do that list to begin with. I do think it depends on your purpose a little bit. So another project we might go into is interstellar medium molecules, and their things don't obey normal valencies. So you can't just use that biosignature list. Creating the list of molecules you want to think about is non-trivial. But if your calculations are pretty quick, you can just add them all in. In terms of astronomically important molecules, about 256 molecules are known in the interstellar medium. Probably, I wouldn't say more than 50 are known in stars, and less than 10 are known in exoplanets. Yeah. So definitely more than the ones that are known to be important. That's the whole point of the whole high throughput. You put everything you can in there, pretty much.
Yeah, and I guess it lends itself to the slightly larger organic molecules where you are relying on the low, or the medium resolution, I should say. Is that right? As opposed to really potentially high resolution for oxygen.
Yeah, exactly. Oxygen, TIO. You do high resolution TIO. The important ones, you do the high resolution stuff. This is for the ones that may be important, the high throughput. All
right. Thank you very much again, Laura. So you've given us a really fantastic talk. It was really enjoyable showing us kind of your research and the teaching and the SciEx project as well. And I think your summary slide wraps it up, and it also said exactly what I had written down to sum up, which was the common thread for me listening to all of this has been about building skills in students, in researchers, and also in the community, in the astrochemistry community. And you've shown us also the value of cross-disciplinarity and collaboration, and also, I suppose, the value of having an attitude of just giving it a go and seeing if stuff works, whether it's a SciEx student doing scary research for the first time, or maybe a chemist talking to physicists. I don't know. I would find that scary. So everyone, please join me again in thanking Laura and congratulating Laura as well. So thanks, Laura.
Thank you very much, everyone.
I might stop the recording if that's okay. And then if anyone else has questions or wants to